Okay, so I didn't show you this, but this is the basic or pure homogeneous transformation. So we did talk about it though. If we have only rotation in our transformation and there's no translation, then this would be your pure rotation because these are zero, right? So you basically are putting your rotation matrix there and give 0, 0, 0 to your translation. So for all three of them. Now, if you have rotation and translation, you mix them. What if you just had a pure translation? Let's say translation around about x-axis. Your rotation matrix is identity. You would just fill in that one element. So if it was only translation about x-axis, you still are able to write a 4x4 matrix. There's only one element that represents this transformation. So transformation is either rotation or translation, right? If you have both of them, then you have a rotation and you have a transformation. So when I say pure or basic, I mean if you had only one type, you still are able to write 4x4. Sounds good? So this is something you want to put your cheat sheet because it has everything in it. So you can bring that to your exam or use that also in your homework. So if you're going to go back to this example, I'm going to try to explain that TAB thing one more time. So hopefully everyone understands. We wanted to express coordinate P in frame A. Now, this is our frame A. We know how point P is expressed in frame B. The 0, 1, 1. We also know the center or the origin here. The origin of frame B with respect to frame A, we have that. So it's a distance, it's 3, right? P in here. Now I want to know how do I express point P in frame A. So we are looking for P in A, unknown. We know PB 0, 1, 1. We also know P translation between the two frames 0, 3, 1, right? Then we also know the rotation between the two frames. We know how frame B is rotated with respect to frame A. So B relative to A, we know that. 1, 0, 0, 0, 0, 1, 0, negative 1, 0. All right. Now to find PA, if you remember from last time, we could say PA is, we know where PB is. We are going to pre-multiply, it's always pre-multiply the transformation of frame B with respect to frame A, or where is frame B relative to frame A. To check, you can see that you're still following the subscript cancellation, right? All you have to do is, let me be lazy. I just learned I can do all these cool things. Thanks, James. I'm not using my iPad as much, so I do, but I didn't know all these. I never used it as a student, so I don't know the magic. So here, mistake. What did I do? What was my mistake here? I need to write T. It has to be 4x4 because I want to represent the rotation and the translation. 0, 0, 0, and then it's 0, 3, 1, 1. This multiplied by 0, 1, 1, 1. This will give me 0, 2, 2, 1. So PA in Cartesian is this, meaning that point P as seen in frame A would be at 0 to 2. So 0 in X direction, 2 in Y direction, 2 in Z direction. Now, I'm going to not to confuse you, but assume a frame attached to you. You're sitting with it, right? Then there's a frame attached to me. I know where the position of this is. You also know the position of this, but only with respect to me and me. To know where this is with respect to you, if you knew the relationship between your frame and mine, as seen in mine, then you can find this in yours. So some of you have problem, why not TBA, right? Because you're trying to find this in your perspective. So you have the information, you know how it is seen in my frame. You want to know how it will be seen in yours. So you have to see how you are being seen in my frame. You have this information. All right, hopefully this should clear things up a little bit. And sometimes you might ask, just for fun, why not from the other frame? Don't confuse yourself. If something is 3 times 2 equal to 4, try to remember 2 plus 2 equal to 4. Don't go all the other ways that it could not be. All right, you're learning a new topic, so learn it the way it is. All right, this technical cancellation is the perfect way of checking if your work is correct or not. Hopefully, with the other example that you're actually going to see at the end of this lecture, this will be solved because you're actually going to see a camera, a robot, an arm, a box. The things should make more sense to you than just simply 2 frames. Now, before we get there, do you remember we had a relative rotation, like 1 frame with respect to the other, and then you had rotation with respect to a fixed frame, rotation with respect to a current frame or body frame, then you post and pre-multiply. Same rule applies for transformation. Because transformation is rotation and a translation. So we follow the same rules. So if transformation T happened relative to the current reference frame, is post-multiply. If it happened with respect to a fixed reference frame, is pre-multiply. Same thing. All right. Current frame, body frame are the same thing. You just call them in different ways. Now, to see why it is important. First of all, the sequence of translation and rotation are important as well. So if you rotate something and then translate, when you're writing the math, the vectors, the matrices, you have to follow which happened first, which happened second. So look at that, the 2 cases. So case 1 here, I'm going to call this case 1. We are going to have first a rotation, second translation about a fixed frame. So starting from S frame is our fixed frame. So this is our fixed frame. We are going to rotate about the Z axis of the fixed frame for 90 degrees. So this is the rotation, and we are going to end up here. Then we're going to translate about the Y axis of the fixed frame. So the whole thing is moved, everything happened about the fixed frame, right? Now, let's say that if we did the same rotation and translation, but about the body frame, meaning that you find the new axis and every time rotate or translate about the new axis that you're in. In case 2, so you have, let's say, let's solve the what if we mix the 2 rotation and translation. In case 2, let's translate about our fixed frame. Let's translate about Y axis of the fixed frame. right? I want to solve, yeah. Y-axis is the fixed frame, then rotate about the axis of the fixed frame. The resulting directions, there are two different frames. So you cannot flip-flop them, say, okay, I'm gonna have, so what does it mean you cannot flip-flop them? When you're multiplying these matrices, you cannot flip-flop them. You have to know the order and then multiply in that order. That's one thing. The other thing is now, if you are doing about a fixed frame or a body frame, so let's say TSP, so B is the body frame, S is your fixed frame. So if you're applying a transformation in a fixed frame, if you are doing a rotation first, so this is pre-multiply, then the translation, multiply by that, right? Now, to find the final transformation, you will write, this is a pure translation, right? So identity for rotation, and then whatever translation was, is 4/4 times rotation. You have the rotation matrix for the 9 elements, and then for translation 0, 0, 0, right? Also 4/4. This was a 4/4. So you are able to do this and get a solution. All right. Now, if we are doing this in body frame, it will post multiply. So this was the original transformation. Now, in this case, I translated first the post multiply and rotated second post multiply because it's in the body frame, and you get a solution. Now, if you want to achieve the same final transformation, you go from fixed frame to body frame, then you might need to flip-flop the order. Okay, you wouldn't know. So it means that there might be cases that you are able to play with the translation and rotation to get the same final transformation. But you have to be careful. That's why in some of class participation, I asked you the visual representation of the mapping you're doing. It can help you to see how things are moving. So it's easier for you to understand, if there is a let's say rotation about a fixed axis, could I represent that if it was about the body frame? What should I rotate to get the same rotation matrix? That's the case. Make sense? So make sure first the sequence, you are following the sequence. Second, you know if it's body frame or fixed. They impact the placement of your matrices when you're doing the multiplication. Yes.
So for those examples on the bottom, it's just translation, rotation. That is one.
So you remember use pure rotation in the first slide as this. So this is a 4/4 matrix. So when you are in transformation, good question, because you have to still be able to do, it has to be 4/4. So we introduced this, a pure rotation. If you are writing it in the form of transformation as the rotation matrix and 0, 0, 0, 1, just fixing the units, right? So be careful with the notations, and whenever you're doing homework exam, you need to explain that. So what is this rotation representing? Is a 4/4 matrix? Is a 3/3 matrix? That's why I always ask you to show your work. So if you don't show your work in your class participation, you lose point. If you don't do it in homework, you lose point. Why am I doing this to you? I'm not mean. I mean, apart from that, I'm not mean, but if you thought so, it's not. Let's say you're working with someone else, right? Usually engineering is a group work. You calculate things, you do something, and then someone else is coming to work with you. They say, give your work and let someone review. They open and say, there's just one matrix as final solution. They don't know what you did. So you want to be able to show your work for someone else to replicate. That's how engineering works. And I'm going to stick by it also. And I try to write as detailed as I can when I solve the problems, so you can follow the same standards. All right. So, example, I want everybody to do this. So this is simple In terms of, I'm just checking if you understood what I talked about, the two things. Building the homogeneous transformation matrix T. So it's 4x4, right? And these are the sequence that things happen. First, a rotation by angle alpha about current axis X. Then there's translation of B along the current axis. So your log, all of them are current axis. So write this, and I'm going to change some of them to fixed axis. But this is like the simple way of solving. Yeah.
So in order to do a transmission and a rotation.
Or just like
Right, so each individually, or is it possible, like, maybe connect?
you can multiply them there right in the. If I called your name, don't be alert, just raise your hand. I just wanna connect faces to names, all right? Audrey? Alexander Vernon? Okay. I think some of your assignment I did be right. All right. Good for you. On my robot. No, from my, yeah, that's it. Yeah, there's another thing. I was totally right on the number. Come on, that's, no. Okay. Y'all got it? So let's write them down. So I'm going to use that same notation. So this is a rotation about X and alpha. We know this is a 4x4, right? This is a translation X and B. This is translation Z and D. This is a rotation Z and theta. They're all current axis, so they're all post multiplied. So again, for those of you that have question about this rotation notation, one, zero, 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 cosine alpha, negative sine alpha, cosine alpha, 0, 0, 0, 0, 0, 0, 1. That will be your pure rotation, right? So the final R, the final T, sorry, is going to be Rx and alpha multiplied by translation X and B, translation Z and D, rotation Z and theta. So So this is a pure translation. B along x-axis 0, 0, 1. Then you basically have two more of this, one more of this actually. This time is 0, 0, D. And then one last one is your rotation, cosine theta, negative sine theta, cosine theta, 0, 0, 1, 0, 0, 0, 0, 0, 1. All right, so 4 matrices, all 4 by 4. So if you did multiply this, it will be 4 by 4. Now, if you have homework or exams that you don't know what the angles are, this is a step. But if I said what alpha is like 30 degrees, this is like 25, the final solution will be a numerical value. You have to multiply. If something was this big, you can use your calculator. If it's homework, you can use MATLAB or calculator. But just put the final solution here. Don't leave it like that. All right, so you could get a numerical solution, get a numerical solution. But here we don't know what alpha and theta are, so we leave it as it is. All right. Now, if the question was like this one was fixed, what would happen? That one would have been pre-multiplied, correct? So you would get translation Z, D, rotation, translation, rotation for a final solution. And your final answer would be a different transformation matrix than this one. So the placement is important. All right, this is the example I was talking about. So this example is in your book. If you have the book, there is another example in the book, which is simpler. If you still have doubt of a perspective of frame A to frame B, I suggest go to the book and solve the example before this. That will help you. Everything is numerical and get a better idea. Now, this one, we want to find the configuration of the object in frame E relative to end effector in frame C. Right? So E relative to C, TCE. You want to know how C sees E? TCE. Now, this is our robot. There is a frame on the body of the robot, frame E. There is a frame at the tip of the arm for end effector, frame C. The object is frame E. The camera is frame D. And you see that we have a fixed frame, corner of the room or in the middle of the room. We don't know. There is a fixed point that everything can be seen from that. That's how they calibrate it. So they calibrate the camera from one point that they know where it is. That one is now. Now we have an unknown CE, TCE, right? But we know a few things. We know TDB. So B is your body frame and D is your camera. So we know how camera sees the body frame and the object. We also know AD, where camera is with respect to the fixed frame, let's say corner of the room. We also know D and E, the body frame and the object. So let's say the robot goes and it knows where it is with respect to C. Oh, see? Okay, it makes more sense. I was kind of why? Because the robot knows the orange, right? I think that's kind of wrong. That's strong. Yeah. Well, there is explanation. Well, we also know the robot frame with respect to the tip of the robot, right? Because you can know. So basically, the problem will be the robot is moving, the robot knows where it is with respect to the camera, knows where the object is. The robot wants to grab the object from with the doesn't know exactly what the object is, but it knows where itself is. But into the camera information would drive itself to the body, to the object, right, and grab it. We want to write that transformation. So once you have all this transformation, the rest is just coding them, and then it will spit out at any time where things are with respect to each other. All right. Now, write a relationship that you can find TCB. There are more than one solution for this, so don't, if you write something and it doesn't look like mine, it doesn't mean it's wrong, all right? Yeah, this is TCB. One relationship is this, right? TAB. So this TBC. Yeah. Huh?
There is no TA.
Okay. Can you find it? We'll try. Do you have TDA and TDB?
There's, I was just thinking like get rid of A. 3D is the line.
Huh?
D is also fixed. Not to get running.
So A is the fixed frame, which is the corner of the room or where everything is calibrated. But when you, so you have the camera, so you have TDB, right? The body from the camera's point of view.
I think I do.
You can't, that's what I said. There is more than one solution. Yours might not be the same as mine. That's the first thing I said. There are different ways because you could do different rotations and find the relationships. That's why I said that's the first thing. You might see a different one. But at the end, our solution should match, right? So one is this, one is TAD, TDA. So basically we are trying to find, so we are going around these two loops, right? We don't have TCE and we're trying to find it. We don't directly have TAB, all right? So we don't panic. We have TBC right here. We have TAD right here. We have TDE right here. Now, can we find a relationship for TAB? Yes. TAB could be TAD, TDB. And we have both of those. Thus, we actually have this. So we can expand and say TAD, TDB, TBC, now TCE, TAD, TDE. In this relationship, we have everything except this guy. Now, this is a relationship we can use to solve. We just have to bring everything from this side to this side and find it, right? Now, there are other ways of finding a relationship for, yes. Good question. That's the next thing. So do you want to say your relationship that becomes CE to CE? So I'm going to write it as if someone else had that when they're studying, they know that's also possible.
So I didn't consider it. I just found, I figured it would be easier to find TEC. So I'm going to find that again.
How did you find TEC?
TEC is equal to TDE, the inverse of that.
So inverse of this?
Yes.
Uh-huh.
Then it's after 30, and then I had T.
What? TDE is not TEC. So what are you multiplying it by?
So then I would have efficiency subtrate, but I would have to match TDD. And then I would do TDD.
Can you read your sentence? I just want to put up here.
Yeah. TDE to the negative 1 times TDD times TDC.
TBC.
TDC, yeah.
So
gives
this
you
is
TDC, and then you can just take the inverse of that
TDC.
whole thing.
And so this is basically TED, right? And TC. All right. You could do that. So there might be other ways that you can follow. All right. I chose this because this had an unknown at the beginning, but then you actually have it. So I want you to know that if you didn't at first sight see it, it doesn't mean you don't have it. See if you can have by extension, right? Okay, now how do we find this? TCE would be re-multiplying the inverse of this times TAD times TDE. Now, what's the rest? What's remain? The groundwork of plugging everything and multiplying them, right? One thing I want you to pay attention is that, you remember I said you can't just get the inverse to put in your calculator. Find this and then use T inverse relationship. All right, we're going to show, at least write what it is. And then if you want to calculate the inverse using your calculator, is fine. So I'll write it here if for those of you that forgot, but this has to be on your cheat sheet. I suggest preparing your cheat sheet as you go and bring it to the class and add more stuff to it. So for exam time, you don't have to write everything from the beginning. Your cheat sheet preparation shouldn't be your study time. All right. So now the rest is just plugging those values. I have it in my annotated version, so you'll see it in this page, all the numbers. I'm gonna just write the final matrix. So you will get to this. So TCE becomes 0, 0, 1, negative square root of 2, 1 over 0, negative 1 over square root of 2, 0, 0, 0, 0, negative 71, 75, negative 260, square root of 2. This is your book, so you can also find this from your book. If there's any mistake, blame your author, but I checked, this is fine. So this is your final solution, your final transformation. E, which is the object, with respect to C, which was the grabber, right? Now, what does this mean? This is a matrix, like our human brain doesn't understand matrix. What is it in real world? What does it mean? Raise your hand so I can pick you and then talk loud so everybody can hear. Don't worry if it is wrong. Yes. Yes, so this first 3, 70, 65, 60, and 130 is the position XYZ of the object with respect to the grabber. So in your code, whatever you're commanding, say go this much in X, this much in Y, this much in Z. So it will be on top of the object, right? Now, then what does this part mean? Well, someone else, you solve half of it. Yes, it is. The arm has to rotate and then do that XYZ. So this is a rotation matrix that we need to find what angles and what rotation cause this rotation matrix. So solving it backwards, right? So you could find an axis and an angle and say rotate, or find polar angle for it, or find XYZ, so pitch roll Y angle for it, and your arm will go there and then grab. So that's inverse kinematics. You know the goal, the location, and then you want to know how to get there. right? So solving backward, that's called inverse kinematic. But you'll see that right now with 3 weeks in, 4 weeks in, you can already solve and find the mathematical solution of the object with respect to your reference. You also know the XYZ. You just need to figure out how to find those angles, right? Because you have different joints, basically like how much each joint has to rotate to get on top of the object. Right? So this are XYZ position. And then this one is rotation matrix between the two frames. All right. So this was the problem I solved. This is the problem you will solve. So start now. Once your time is up, if you can find it, continue at home. If you found it, you submit and you're good for Friday. I'll be here for the next 15 minutes. Because it's open until Friday. Yeah, I could take your English, you said me. That's fine. I was like, I'm walking to you, what is your next? You two are both Jacob.
I mean, it's still. Yeah. I guess. Yeah.
Minutes of nothingness. So sorry for, I know nobody watches these things, but you know.